This is lecture number 1 of week number 7, in which we will continue with the remaining two psychrometric processes, that is cooling and dehumidification, and after that chemical dehumidification. The cooling and dehumidification process is a very important process in air conditioning, and now let's move on to that process and the details of that process. So what we have physically is that there is a cooling coil in which we have a cold fluid circulating inside tubes, and air at a relatively high temperature is made to pass over that cooling coil. The surface of the cooling coil is maintained at a temperature shown to be Td, and the entering air temperature is T1. And because we want the air to be dehumidified, the temperature of the cooling coil must be below the dew point temperature of the incoming air for condensation to occur. If you had ideal conditions, the air would come in at a dry bulb temperature of T1, it will be perfectly cooled and it will leave at a temperature Td. But the heat transfer process is not ideal. There are temperature gradients across the air. You will, when you study convection in details, you will see that there is a thermal boundary layer as well, in which temperature gradients are present. So it is not that all the particles of the fluid are cooled to a uniform temperature. Those closer to the surface are cooled more, and away from the surface their temperature is slightly higher. That means when the air leaves the coil, it is actually at a temperature higher than Td, and that is shown to be T2. So if we look at the representation of this process on the psychrometric diagram, the actual process line is shown by the curved process line, but it can be represented as a state, that is state 2, which results from the adiabatic mixing of two air streams, one which is at a temperature T1 and the other which is at a temperature Td. And we will see later on how this actual process can be considered to be replaced by the process of adiabatic mixing of states 1 and D. The coil surface temperature is also referred to as the apparatus dew point, and generally represented by the symbol, not the symbol, abbreviation ADP. And for a cooling and dehumidification process to occur, the apparatus dew point must exist. The energy balance we can work out quite easily. If you again look back at the psychrometric diagram, we have a higher energy content over here and a lower energy content at state 2. So what will happen is that energy will be removed from during the process, and at the same time condensation of the air will occur. So that can be represented by the equation m dot a into h1 minus h2. So that means incoming air had an energy content m dot a h1, and you had minus q over here because energy was being removed from the air. So if we take that minus q onto the other side, that becomes q. This is the rate at which the cooling coil is removing energy from the airstream, and because there is condensation, the fluid which condenses also carries with it energy that is equal to m dot w plus hw, and what remains is the energy at the end of the cooling process, that is m dot a into h2. So if we had a first equation, it would have been m dot a into h1 minus q dot minus m dot w hw, because that was the energy that was leaving your control volume, and then on the right hand side you would have m dot a into h2. So we just rearrange that equation, and that gives you the energy balance equation for a cooling and dehumidification process. If we look at the mass flow balance on the water in the air, that is along the lines that we had done earlier, that means the humidity ratio was higher at state 1, it is lower at state 2, and the difference is because we have removed or condensed water out of the airstream. So we will simply write the equation, that is m dot a into w1 minus w2 is equal to m dot w, and m dot w is the rate of condensation. And we can combine the above two equations to get a single equation for the capacity of the cooling coil. And if we look at the equation, it has two terms, one which relates to the change in the enthalpy, and the other is related to the energy carried by the condensate. So usually the rate of condensation is small, and the second term on the right hand side can be neglected. So you can approximate the capacity of the cooling coil by the equations, simply by the equation that is Q is equal to m dot a into h1 minus h2. But if you want to be accurate, you can keep the entire equation as it is. Then we define what is known as a bypass factor. Now before I go to the bypass factor, I will come back to that point that I had made earlier, that the actual process can be considered to be a combination of two streams, one at state 1, the other is at state D. And for that, let's look at this cycle, the process, and a schematic representation of the system, that is flow of air over a cooling coil. As I said, the air particles are not at a uniform temperature in the airstream. Those closer to the cooling coil are at a lower temperature, those away from the cooling coil are at a higher temperature. What we can do conceptually, we can say that we can divide this non-uniform air temperature distribution into two parts, or a combination of two parts. One part in which the air is assumed to be perfectly cooled, that means all the particles of the air in that particular stream are cooled to a temperature Td, and we can assume that the remaining particles are not at all affected by the cooling coil and they remain at the temperature T1, as if that portion of the air has bypassed the cooling coil, and that is from where the term bypass factor is derived. So if you look at this figure over here, you can see that if we consider the incoming air, which has a mass flow rate of m dot a, it is divided into two parts, one which is unaffected by the cooling coil, which bypasses the cooling coil, so that is stream B, and the other stream is which is perfectly cooled to a temperature Td, which is shown as the stream D. And after the two streams have passed the cooling coil, they are mixed adiabatically, and that is where we apply our earlier result of adiabatic mixing of two air streams. M dot A is at a temperature T1. You can see over here. This is M dot A over here. And M dot and the other stream is at a temperature TD. And if we adiabatically mix two air streams, 1 and D, and we are saying is that at the end of the mixing we will still attain the same temperature that actually exists in the cooling coil, that is state 2. So you can say that state 2 must lie on the straight line connecting states 1 and D based on our earlier analysis of adiabatic mixing of two air streams. That means that although the actual process line is shown by this solid line over here, but the state point 2 we can still obtain that state point. That is what we are more interested in, end point of the state, that can be obtained by applying the concept of bypass in the cooling coil. So that is how we replace or simulate the actual process by dividing the airflow into two streams, one which is unaffected by the cooling coil and the other which is perfectly cooled by the cooling coil, and then the two streams are mixed together to get the same state as the actual state. So if we look at this figure over here, the difference between temperatures T2 and TD, that shows the effect of the bypassing of the cooling coil. If the air was perfectly cooled, that means state 2 would have coincided with state D, but because of the actual cooling in which temperature gradients are present, the air will leave at a temperature higher than the coil temperature, and that effect is represented by a bypass factor. The bypass factor then is defined to show the effect of the imperfect cooling of the air, and it's the ratio of the bypass effect divided by the ideal case in which the air, if it had been ideally cooled, would have gone through a temperature change T1 minus TD, whereas T2 minus TD in the numerator shows the effect of the bypass. We can also find out the bypass factor by using the humidity ratio or the enthalpies, but it is usually more convenient to use the dry bulb temperatures. The contact factor is just the opposite of bypass factor. It shows how efficient the coil is, and that will be 1 minus the bypass factor. The sensible heat factor is defined as the sensible heat load by total heat load, and this factor will exist for any process in which sensible as well as latent energy transfer takes place. And we will move on to an example based on the cooling and dehumidification process that we have studied. We are given the condition of air which enters at a cooling coil at a certain flow rate, and also the condition of the air when it leaves the cooling coil, and we are asked to find out the capacity of the coil, the sensible heat factor, bypass factor, and we assume the condensate water to leave the coil at the apparatus dew point. As before, we identify the process by reading the problem statement. then sketch it on the psychrometric diagram, label it properly, and then we proceed with the actual solution. Because the dry bulb temperature and relative humidity of the air is given, we can easily locate state 1, and similarly we can locate state 2 using the dry bulb temperature and relative humidity. So that is straightforward. Once we have done that, we can then find out the specific enthalpy and the humidity ratio at state 1, and the same can be done for state 2. And I will go to the psychrometric chart, actual psychrometric chart in a while, and show you how I have got these values over there. So remember, what we need to do is first we need the cooling capacity of the coil as well. So before that, we will also locate state D, which is quite straightforward, because if you have already located states 1 and 2, state D can be easily obtained by extending the process line 1 to 2 to the saturation line. And once we have reached state D, we can find out the apparatus dew point or the temperature at D, and that is now shown on the actual psychrometric chart. You can see I have already located state 1 and I have located state 2 using the properties given in the problem. At state 1, 50% relative humidity and 25% dry bulb temperature. Similarly, at state 2, you have 11 degrees C is the dry bulb temperature and 90% is the relative humidity. And you can see I have extended the process line 1 to 2 to the saturation line, and at that particular point, if we read at the temperature, this is 5 over here, this is 6, 7, 8, around 8.5 degrees is the temperature at D, and that is what we have got in the solution. Once we have got located the state D, we can then move on to the capacity of the cooling coil and use the result that was obtained earlier by the energy balance, that is Q dot is equal to m dot A into H1 minus H2 minus m dot A W1 minus W2 into HW. In this equation, as I mentioned earlier, usually the first term is quite large and the second one is small, and we can almost approximate Q dot by m dot A into H1 minus H2. But to just emphasize that point, that the relative magnitudes of the two terms are quite different, we will use the full expression. Now HW will be obtained from table A1, that is properties of water, and we are told in the problem that the condensate leaves the cooling coil at the apparatus dew point, that is at temperature TD. So HW will be equal to HF at 8.5 degrees C. That's why we need to obtain the temperature D before we proceed to this equation. That is obtained from the table. Then we have got the values of H1 and H2 from the actual psychrometric diagram. You can check those values. That I'll just go back a little. H1 is 50.5 and W1 is 10. Similarly, H2 is 30 and W1 is 7.5. If we want, we can look at these. I've already marked these out over here. You can see that this is H2 is around 50.5, H1 is 50.5 and W1 is around 10 grams per kilogram dry air. Similarly, if you look at H2, it is 30 kilojoule per kilogram dry air, the specific enthalpy, and the humidity ratio is 7.5 grams per kilogram dry air. So we go back to the cooling coil capacity, and you can see the first term has a value of 41 and the second is around 0.18, which is quite small, and even if we had neglected this, it would not have changed the coil capacity value by any significant amount, so that is acceptable, and we get the cooling coil capacity as 40.82 kilowatts. Okay, the sensible heat factor, again we can make use of the protector over here, because we have already got the process line 1 to 2. All we have to do is to draw a line parallel to line 1 to onto the protector and read of the sensible heat factor value from the inner scale. And if you look at it, this the process line 1 to 2 is also is drawn in the protector. That means this line over here in the protector is parallel to line 1 2, and on the inner scale we have the sensible heat factor, sensible heat by total heat, so it is around 0.69. That is, sometimes we can move from the protector into the chart, and sometimes from the chart you can move to the protector to read the desired value. That depends on the problem that you are solving. So that is the sensible heat factor, and the last thing that was required was the bypass factors, and we can use the temperatures quite easily to obtain the bypass factor. T2 minus TD, we have already got similar divided by T1 minus TD. We have got all these temperatures, substitute those values, and the bypass factor comes out to be 0.15. That is around 15% bypass effect. The last process that we are now going to look at is the heating and dehumidification process, which is also known as chemical dehumidification. And this process is carried out by passing air over a material which has an affinity for moisture. That is a hygroscopic material which can absorb or adsorb the water vapor from the moisture. And typically the substances that are used for this purpose are solutions of calcium chloride, lithium chloride, lithium bromide in water, and similarly ethylene glycol in water. These are known as brines. We can also use crystals of silica gel and also activated ammonia. Generally this process is a process in which heat is released. So the dry bulb temperature, you can see the actual adsorption dehumidification shown on the cyclometric diagram. If you have adiabatic dehumidification, it will follow a constant enthalpy line, in which of course the dry bulb temperature will be changed, will increase. But if you have the actual adsorption, that means it will release further heat, so it's exothermic, and so the dry bulb temperature will be further increased. So the utility of the chemical dehumidification process is that it is used in combination with the actual refrigeration of the air. That is, it will remove the latent load, or it will reduce the latent load on the cooling coil. Now if you just go back to the previous case of cooling and humidification, all the dehumidification is carried out by the cooling coil. Now if we have chemical dehumidification prior to the cooling and dehumidification process, part of the latent load will be taken up by the chemical dehumidification process, so the latent load on the cooling coil will be reduced. Having studied the processes, we can now combine these processes to form cycles, and the two principal cycles that we will study are the heating and cooling cycles. One for winter air conditioning, that is the heating cycle, and the other for summer air conditioning, that is the cooling cycle. And you will see that this cycle will be formed by combining the processes that we have studied earlier. First, I will describe the schematic of the heating cycle. You can see that we have the space. This particular part shows the conditioned space in which we want to maintain a certain temperature and humidity ratio, or a relative humidity. And because we are talking about the heating cycle that's in winter, this space, let's say it's a room or a building, will be at a higher temperature and humidity ratio compared to the air outside. In winter, the air is cold and the humidity ratio is low. As a result, what will happen? There will be a heat loss, both latent and sensible, from the conditioned space to the surrounding or ambient air. And to maintain the desired temperature and humidity ratio in the conditioned space, we will have to provide air which is warm or heated and humidified to the space, so that this particular air which is heated and humidified balances the loss, both latent and sensible, from the conditioned space and maintains it at the desired state. The state inside the space is represented by the letter R. So R represents the state of the air in the conditioned space. The S shows the state of the supply air. So when we supply air to the conditioned space, it will be, if let's say if the temperature inside the space, I'll just put in a figure. Let's say the temperature over we want is 25 degrees C, and the relative humidity we want is 50%. That is state R. That means we will have to supply air at a higher temperature and a higher humidity ratio, so that even after we have latent and sensible loss, we are able to keep the temperature at 25 degrees C and 50% relative humidity. Then that air which is in the room will be again returned or recirculated to the cooling coil, to the heating coil, and it is humidified, so that we have a constant cycle in which the heated and humidified air comes into the space, maintains it at the desired temperature, and when this heated and humidified air loses latent and sensible heat, it still maintains the desired conditions in the space. You can see also that there is an exhaust and fresh air shown in the schematic diagram. The reason for that is, of course, one thing that we could have done is that you take the outside air, heat it, humidify it, supply it, and then exhaust the air. But that is very much energy inefficient, because the energy that you are supplying in the coil and for humidification, all that will be then exhausted, and you will have to start afresh. That means the outside air, let's say, is at 10 degrees C and it has a very low humidity ratio. Then you start from 10 degrees C and take it all the way up to, let's say, 35 degrees C. Then that air is cooled to 25 in the space, and then you exhaust that. Now it is much better to recirculate that air which is at 25 degrees C and then heat it to 35 degrees C. That very much reduces your energy consumption, and that is much more energy efficient. You could have said that we could have then recirculated 100% of the air. Why go through an exhaust process? Now the exhaust is required because we also want to maintain the air quality. If you have a conditioned space, which is a closed space, let's say there are people sitting over there and there's equipment running and there are furnishings inside the room, etc. When it is occupied, there is a buildup of carbon dioxide. When people breathe out, there is odor that is also generated. Then the various equipment or furnishings also release chemicals slowly over time, even carpets, paints, etc. in the wall. So if we keep on using the same air over time, those contaminants will build up, and that is not desirable. So we want to maintain the contamination level inside the room or the indoor air quality at a certain level, and to do that we exhaust part of the air which is being taken from the conditioned space and then mix outside fresh air with the recirculated air, and that is shown by this letter M over here. Now let's again start right from the beginning. You have the supply air going into the conditioned space at a temperature and humidity ratio which is higher than the desired state in the conditioned space to balance the latent and sensible heat losses. The space is at state R. Now that air which was supplied is returned from the room, part of it is exhausted and part is recirculated and mixed with the outside air. So after we mix states R and O, the resultant state will be state M. That state M will then be heated to state H and humidified and supplied at state S to the conditioned space. This can then be represented as a cycle on the psychrometric chart, and that is shown over here. As I said, typically the outside air is cooler and drier than the air or the state that you want in the conditioned space, that is a state R. So you can see that O is at a lower dry bulb temperature and a lower humidity ratio. Similarly, state R, that is the desired state in the conditioned space, is at a higher temperature and a higher humidity ratio. So the air which is mixed at state R with state O will be at state M, a diabatic mixing of two air streams. The resultant state M must lie on the straight line connecting states R and O. Then that air is heated and humidified. So we have studied the heating and humidification process. You can see this is the sensible heating carried out by the heating coil, and then there is a humidifier which increases the humidity ratio, and typically we use steam for humidification purposes, so that also leads to a slight increase in the dry bulb temperature. Once you have reached the desired supply state, that is S, then you will supply it to the room, and in the room you can see that because of the heating load you will have the heat being the latent and sensible heat, which is basically being lost by the room, and that is balanced by the supply air to the conditioned space, so that this room or conditioned space is maintained at state R. If we had supplied the air at state R directly, what would have happened is that because the air is losing heat to the air outside, we would not have maintained state R. The temperature and the humidity ratio would have dropped further. So that's why we have to supply air at a higher humidity ratio and a higher temperature. That is the basic cooling cycle. There are of course modifications to improve this cooling cycle, but we are not going to go into that. We will just confine ourselves to the basic heating cycle, and that is for winter air conditioning. The line SR is known as the space condition line or the load ratio line, and that shows the load of the conditioned space. So if you were to ask to if you need to find out the rate at which energy is being lost from the conditioned space, we can multiply the mass flow rate of the air and multiply it by HS minus HR. That will be the heating load for the conditioned space. Then we move on to the basic cooling cycle, which is applicable for summer air conditioning, and similar to the heating cycle, we have a schematic diagram showing the conditioned space, and this time, because we are talking about summer air conditioning, the conditions outside the conditioned space are warmer and more humid, so there will be a cooling load which has to be balanced by the supply air. So we have a supply air. This is the space which will be at state R, and you can see from the space the air is returned, part of which is exhausted. The recirculated air is mixed with the outside air, which is at state O. The resultant state is again shown by the letter M, and then because we are talking about summer air conditioning, the mixed air will then be passed through a cooling and dehumidifying unit to dehumidify and cool the air to state S. And this time, because there is a latent and sensible load on the space again, the supply air conditions would be that the dry bulb temperature will be lower than the temperature, and the humidity ratio will also be lower than the humidity ratio that is required in the space, so that after the heat gain, both latent and sensible, we are still able to maintain the desired state R in the conditioned space. Okay. And as we did before, we can then represent this on the psychrometric diagram, and you can see again we have shown those processes over here which combined together form the cooling cycle. If you look at the outside air, it's shown by state O, which is at a higher humidity ratio and a higher temperature than the desired state in the conditioned space, which is shown by the letter R. The adiabatic mixing of the two air streams gives us the mixed state M, and that air which is at state M passes through the cooling and dehumidification coil until the desired state S is obtained. So M to S is the cooling and dehumidification process, corresponding to which apparatus dew point must exist, which is shown by extending this process line M to S to the saturation line at state D. So that is the apparatus dew point. Now the air at state S is supplied to the room, where it will gain both latent and sensible heat, resulting in an increase in the dry bulb temperature as well as the humidity ratio, and the air is supplied such that it balances the cooling load for the space. That is the basic cooling cycle, which is for summer air conditioning, and that is typical of the cycle that you would come across in the region that we are living in. And again we had the load ratio line, that was line SR. Next we will take up an example based on the cooling cycle. The problem statement provides us with the sensible and cooling loads for the given space, the space state in terms of the dry bulb temperature and the relative humidity. The outside air state is given in terms of the dry bulb and wet bulb temperatures, and there's some information about the amount of the outside or fresh air that is used with the recirculated air to provide the desired supply air flow rate to the conditioned space. And we are asked to find out the volume flow rate of the air that is supplied to the space, the coil apparatus dew point, bypass factor, and the capacity of the cooling coil in terms of refrigeration. Because the cooling coil or because the space loads are given separately as the sensible and latent loads, we can find out the sensible heat factor. Of course, when we move to the psychrometric chart, we will try to obtain this cycle. That should be the objective, that if you are able to locate all the state points of the cycle on the actual psychrometric chart, then we can find out any answers that we need for the given cooling cycle. And similarly for a heating cycle, the objective is to locate all the state points. Because the state points O and R can be easily located, that is the first thing that we will do when we go to the actual psychrometric chart, and corresponding to those state points O and R, we will be able to read of the specific enthalpies. The values will be shown to you later, and I will also show you those on the psychrometric chart. The sensible heat factor, as I said, we can find out using the sensible and latent loads. So the sensible load divided by the total load gives you a sensible heat factor of 0.78. Once we have got the sensible heat factor, then we will be able to locate state S using that sensible heat factor and the temperature, the dry bulb temperature of given in the problem for state S. How we will do that, locate state S? When I move to the actual psychrometric chart, you will be able to see how I have done that. And once you have located state S, we will find out the specific enthalpy, and we will also need the specific volume at state S. Then we will use the energy balance for the cooling load, that is Q dot for the space which is given to us as 9 plus 2.5, that is 11.5 kilowatts. That basically is for this part of the cycle in which the load causes an increase in the enthalpy from state S to state R. So we will have the enthalpy difference HR minus HS, and that will be multiplied by the mass flow rate that is supplied to the conditioned space m dot AS. Because we have located states O, R and S, you will see that we will be able to find out the mass flow rate in terms of kilogram dry air per second. And once you have the mass flow rate, and we also know the specific volume at state S, then the volume flow rate is simply the mass flow rate times the specific volume, which comes to 0.6 cubic meters per second. Now I will go to the psychrometric chart and show you the steps that we have gone through up to this point in the solution. You can see I have already worked out the problem. So the first thing I did was I located state O, then I located state R. And remember, the objective is to locate all the state points and then complete the cycle. We know that the process O to R represents the adiabatic mixing on which point M will lie, so I will connect state R with state O by a straight line. And you can see we can read of the specific enthalpies for state R and similarly for state O from the given scale. The next thing that we had to do was to locate state S by using the sensible heat factor and the dry bulb temperature of the state, which is given in the problem as 12.5. Not the supply air is at 12.5 degrees C. So you can see I have got this line over here which is at 12.5 degrees C over here, but I need some other information using which I will have to locate state S, and that is the sensible heat factor. So what I did is, first I went to the protector and I drew a sensible heat factor line which corresponds to the conditioned space, that is the space condition line, which has a value of 0.783. You can see the value. I've drawn that line on the psychrometric chart over here on the protector, and we know that the space condition line connects states R and S. So if I draw a line parallel to this line from R, state S must lie on this line. Where on this line it will lie, that was determined by the dry bulb temperature given to us. So first I drew a line from state R which was parallel to the space condition line which I had drawn on the protector. Then I used the dry bulb temperature at state S, and the intersection of these two lines provided us with the state S. Once we have state S, we can find out its specific enthalpy and the specific volume. You can see I have marked those over here. This is the specific enthalpy, specific volume line of 0.82 meter cube per kilogram dry air. Okay. Then we now have states S, R and O. The next state that we need to obtain is state M, and we know that state M will lie on the line OR. If you go back to the schematic diagram, I'll go back to the schematic diagram for the cooling cycle, and you can see the mass flow rate that is supplied is the same as the mass flow rate that we obtain after mixing of the recirculated air with the fresh outside air. So if let's say if R is 1 kilogram per second and O is 0.5 kilogram per second, M will be 1.5 kilogram per second, and the same mass flow rate passes through the cooling unit. And remember, this is the mass flow rate of the dry air, so there's no change in this mass flow rate once it passes through the cooling unit, and it will be the same at state S. So that is what is stated over here, that the mass flow rate of dry air at state S is the same as the mass flow rate of dry air at state M. And in the problem we are told that the outside air, the supply air contains 33% by mass outside air, that is the outside air is 0.33 times the amount in the supply air. Remember, the supply air mass flow rate will be greater than the mass flow rate of the outside air that is used for mixing with the recirculated air. Similarly, the amount of recirculated air will be also less than the mass flow rate of the supply air. The sum of the outside air and the recirculated air will be equal to the mass flow rate of the supply air. So if the mass flow rate of the outside air is 0.33 times m dot as, that means the remaining 0.67 times or 67% will be the outside air. So the outside air, oh, it will be the recirculated air. So the recirculated air is 0.67 times the mass flow rate of the supply air, and because the supply air is the same as the mixed air flow rate, so I have replaced m dot as by m dot am. Then we can perform an energy balance on the mixing of the two air streams at states O and R, and that we have done. In the solution, we will replace the expressions for m dot ao and m dot ar by the equivalent expressions, in which we have m dot a as 0.33 times m dot as, and similarly m dot, we will replace them by these expressions. Instead of s, we can have m dot as, we can have m dot am. So having replaced those, you will see that the terms m dot am will cancel out on both sides of the equation. You will get 0.33 times h outside plus 0.67 times h for the space, and that will be equal to hm. We know the values of hr and ho, and that will give you the value of hm, which comes out to be around 52.6 kilojoules per kilogram dry air. Once we have got the value for hm, then we can use that value to locate state m on the line OR, and after locating state m, we can find out the dry bulb temperature at state m, which comes out to be 26 degrees. And let's see how we have done that. You can see I have marked this enthalpy constant specific enthalpy line of 52.6, and when I extend this line onto line OR, the intersection of this line with line OR gives us state m, and then once we have located state m, we can read the dry bulb temperature over here, which is 26 degrees C. We were asked to also find out the apparatus dew point, and again that can be easily done because now we have both state points m and s. So all I have to do is to extend the line ms up to the saturation line and then read the temperature at that point, which you can again see has been done at the apparatus dew point shown by the letter D. We have got the temperature, which is, this is 5, 6, 7, 8, 9, and this is 9.5 degrees C. Okay, so that is the apparatus dew point, and then we can find out the bypass factor. Remember, the bypass factor shows is the ratio of the bypass effect to the ideal cooling range. So if I look at this diagram, previously we had used numbers like T1 and T2 or TD for that. Now we have letters, so we can use those letters to represent the bypass factor. In the numerator you show the bypass effect, and the bypass effect will be the temperature difference between state S and state D, so it will be TS minus TD. And in the numerator you had the ideal cooling range. If the air had been cooled ideally, it would have been cooled from state M to state D. So in the denominator we have Tm minus Td. We have all the temperatures at these states, and once we substitute those values, we will get the value of the bypass factor, which is around 0.182. And then finally we need the cooling coil capacity, and the cooling coil capacity is obtained by multiplying the mass flow rate that passes through the cooling coil, which is m dot am, into the enthalpy difference that occurs across the cooling coil. The enthalpy difference across the cooling coil is from state m to state s, so hm minus hs, and that comes out to be 4.13 tons or 14.52 kilowatts. Now one thing that you will notice is that the coil capacity is 14.52 kilowatts, whereas the space load was 9 plus 2.5, that is 11.5 kilowatts. So the coil load is higher than the load on the space, and the reason for that is that this coil is also used to bring the outside air which is mixed with the recirculated air to the desired supply condition, and the outside air is much more warmer and humid compared to the recirculated air. That is, there is an additional load on the coil because of the outside air which is being cooled to the supply state. That is why the load on the coil will be greater than the space load.